Before I begin, let me thank the organizers for this opportunity to talk, and I understand it's almost the end of the day and we are all tired. And actually this was supposed to be in another session, but this is clubbed to this, but anyway at least we get to hear different types of talks. And yesterday and day before yesterday, those of you who are attending, you could have listened to lots of talks on two-dimensional materials, particularly the Moir system where you stack different two-dimensional materials. So today I want to talk about as a continuation of those talks. So I have not put much of introduction, but I would just elaborate as I go along. So I want to particularly emphasize a few aspects that can be actually exploited using a technique called Raman spectroscopy, which was discovered in this land way before our independence. In fact, that is still the first Nobel Prize from India, and that continues to be the last Nobel Prize for people working in India. Right? Okay, so what I want to talk about, I will talk about thermal transport, especially how do you measure thermal conductivity in low dimensional systems, particularly in two-dimensional systems. Then I will talk a little bit about the exciton-phonon coupling, and then I will talk about phononics, what is called the Moir phononics, where we have different types of lateral heterostructures stacked in horizontal as well as vertical direction, and how by changing or twisting different angles you can tune the excitons, the phonons, and their collective interactions, right. So this is where I come from. I come from this Kalinga Institute of Industrial Technology, which is a private university in eastern part of India, that is in Odisha, and this is a beautiful campus, and you can see it's a big campus is part of this, and this is where our students are actually working. This is our central research facilities, and these are my students whose work actually I will be talking. And before I begin, let me thank the funding agencies, and I do not actually prepare any material. So all the material that I will be discussing here actually are fantastic materials made by my collaborators from Institute of Physics and IIT Kharagpur, Prasanna and Satya Prakash and his students, and two of my PhD students who are involved in the work that I will be discussing, right. All right. So now I don't want to get into a detailed outline and all that, so I will just go along. So why heat transport, managing heat becomes very important at a nano scale. We all know that as we work, as the civilization is developing or evolving, the size of the devices is getting miniaturized, and we are basically putting lots and lots of transistors into a very small tiny volume, right. And this is, you all know, this is the Moore's law, and the number of transistors that is being put into a smallest volume keeps on increasing. So therefore one has to be careful about how do we manage and transport heat in a world that is ever shrinking, right. So that's the idea, and how do you understand about heat transport, right, and why this is important. If you are looking into high power electronics, batteries, photovoltaics or thermoelectric energy conversion, managing the heat is very, very important, right. So what is important, if you understand the thermoelectricity, there is something called a dimensionless quantity called figure of merit, and in this figure of merit it is very important that to measure the thermal conductivity. If you have a bulk system, it is fairly straightforward how to measure the thermal conductivity, but when you are looking for low dimensional materials, it is a challenge actually to measure, because there are several issues that crops up. And long back there was this paper where they say that if you make nanowires, the thermal conductivity can be largely suppressed, and a suppressed thermal conductivity is good for a thermoelectric material, because here it appears in the denominator. So one can actually increase this figure of merit, okay. But we are not, I am not going to discuss about how to increase the figure of merit. My idea is actually how to measure the thermal conductivity in a low dimension system, particularly with reference to using Raman scattering or Raman spectroscopy, right. So this is a paper where they have actually measured the thermal conductivity of silicon nanowires using a different technique, and we try to measure the same thing using Raman scattering, and how it is done, that is what first I will discuss before I get into two-dimensional material. So this is a quick introduction to those of you who understand heat transport. So if you want to understand how heat is actually transported, you have to understand what is the thermal conductivity. So you have to understand the Fourier law, where the heat always flows from a hot end to a cold end, and this is how the thermal conductivity actually comes into picture. So, the amount of heat proportional to the gradient of the temperature, and the proportionality constant comes, and that is the thermal conductivity, right. And if you want to write down the diffusion equation, this is how it looks like. So, the specific heat appears here, the thermal conductivity appears here, and the heat conduction is essentially the rate of change of the energy that is being stored, right. So, now this equation, this diffusion equation actually holds good, especially when you are scattering mean free path of the energy carrier, where T is much greater than T. So, there is a little symbol problem here, and the mean free path of the energy carriers is actually small compared to the length of the system, right. But if you want to apply this diffusion equation to a low dimensional system, then this would not actually apply. Okay, so one has to change by what so to speak about the quantum limit, right. And if you just go to the textbook understanding of your heat transport, you know these are the quantities that decide. So, there will be this kinetic theory, if you do, this is the specific heat, this is the velocity, this is the mean free path, and one can actually rewrite this in terms of the the mean the time involved and the velocities, right. And this is all textbook stuff. So, what plays an important role as far as phonon scattering is concerned, that is what is decide these velocities and the time. So, boundary scattering, defect, dislocation, phonon scattering, and all that is what is going to decide. Now, this is how it looks like. Now, question is, how do you measure the thermal conductivity? There are many existing techniques, including the 3 omega, the MEMS, and the TDTR method. These are all okay when you are doing bulk systems, but if you want to do with a low dimensional system, one has to work with this MEMS, which is actually quite intensive in terms of fabrication, etc., but it has its own problem of thermal contact resistance. But here comes the power of Raman, where Raman can be actually used to measure the thermal conductivity of these materials, and this is how I would just quickly show. So, how does actually Raman help in this? So, this is actually like say ek goli mein do shikar. So, you have the same laser which is being used to collect the Raman spectrum, and the same laser is actually being used as a heater. So, you use the laser to heat up your sample, and you look at the phonon spectrum, and you see how actually it shifts as a function of either you increase your laser power or you increase the temperature. This is how you do. So, and once you know how this temperature coefficients or the power coefficient of the Raman shift, that is d omega by dp or d omega by dt, that you can model your heat transport, and then that is how you understand you can calculate the thermal conductivity, right. So, this is something that we did I think in 2020, where we measured the thermal conductivities of silicon nanowire, but today's talk is on 2-dimensional material. So, I will see how we extend this into other systems, right. And this is how you do. So, this is basically a freestanding nanowire, and then this is what you do from this diffusion equation. This is the modeling. What I want your attention to be drawn is, this is d omega by dt, that is the temperature coefficient of the Raman shift, and this is d omega by dp, that is the power coefficient of the Raman shift, and there are other quantities like for this system what is the length and what is the diameter, etc., etc., and you calculate effectively, though the laser is falling, not the entire laser beam is falling onto your system, what part of the laser is being used to heat up your system. So, that is something that you calculate, and then of course you model, and then find out what is the thermal conductivity, and then we see that we measure somewhere the thermal conductivity somewhere here, and this is from the MEMS measurement, which is not bad if you compare from the other technique, considering the simplicity of the technique and other constant that is actually present in this kind of systems. Now, this is what we have done in silicon nanowires, but in my title it was about 2-dimensional material. So, if one has to move beyond silicon, because these days 2D materials are very promising materials, and if one has to use them in devices, one has to understand the heat transport, thermal heat management, etc., in these systems, and I do not think we need much introduction into this system. These transition metal dichalcogenate, you can see this entire periodic table where you have chalcogens and the transition metals, and they are unique in the sense that their thickness is few atomic layers or one atomic, and in the monolayer limit they have a direct band gap, means they can actually emit. So they can be used in display devices, and because of the involvement of these transition metals, you have a strong spin orbit coupling, and you can have many interesting like electronic and mechanical properties that can be tuned by varying, and you have lots of possibilities of playing with different transition metals, and it is known that there are many class of transition metals, 2D materials, including the insulators, semiconductors, and superconductors, etc., etc. So I would largely focus on to the TMDs, that is transition metal diazote chloride. And here I just want to tell you for historical context, the story of this transition metal diazote chloride started with the discovery of graphene. But if you compare graphene with the transition metal dichalcogenide, the major difference is that graphene only has a single structure. But if you compare with the TMDs, so they can actually occur in various polytypes. You can think something like the polymorphs, for example. So you can have this T phase, the H phase, the hexagonal phase, and the rhombohedral phase. So these are basically the number of units 1T, 2H, and 3R, right? So basically it's the same thing, but the structures are different. And Raman also plays an important role in distinguishing this 1T from the 2H and 3R, and each of them have their own importance in terms of their applications in different fields, right? So again I will come back to the thermal conductivity measurement, and this is what was done in one of the work by Reg and others which was published in 2022. So we were interested in this kind of systems, and then try to see how to extend our work and in measuring this thing. Okay. So now this is as far as the transition metal dichalcogenides are concerned. Now you can always take them and then kind of stitch in the lateral direction, so that becomes lateral heterostructures. You can actually put them one over the other, stack it, so that is a vertical heterostructure. You can have a combination of lateral versus vertical. You can have different combination, which I'll talk in towards end of my talk. And that would have lot of freedom. Again, you can play with the excitons and their binding energy. There could be charge transfer and so on and so forth. And one can actually do exploit these attributes in enhancing many different properties for different device applications, right? And you can have directional heat transport and all such things, right? So then let me come back to our initial discussion of what is called the thermal conductivity measurement in a bilayer, and in this case the bilayer is tungsten sulfide. So this is the transition metal is tungsten and the chalcogen is sulfur. This is tungsten sulfide. This is something we published last year, and let me discuss what exactly we have done, and again I will always relate to the Raman spectroscopy in these systems. So what you see here, these are actually WS2 systems. These are grown by something called salt assisted technique, CVD method. It is grown by Satyaprakash and his students. So what you see here, this is basically the structure. These are the blue ones are tungsten. This is sulfur. This is the optical microscope picture, and this is actually what is called the A1G mode, which is mapped across the sample. So this is the Raman intensity of the A1G mode. So this the TMD, they're quite rich in their spectrum, and you can just characterize them. But what is interesting here, you see there is this red one is 3R, and the black one is 2H, and the blue one is monolayer. Okay, but I told you this is a bilayer, so WS2 over WS2. So this is two layer system, but then there are two different phases present here. One phase is 3R, the other phase is 2H, and we can actually distinguish them from their Raman signatures, which one is 3R and which one is 2H. So this Raman actually helps you to distinguish in the same sample. There could be regions where it is grown in the 3R phase, and there are regions where it is grown in the 2H phase, right? So that's something, this thing. Now you can ask me, how do you know there are layers stacked on each other? So because there will be a interlayer interaction, and there could be something called a shear mode and the interlayer breathing mode. So that is being captured in something called the low frequency Raman, which is basically the low frequency region of your Raman spectrum. So the presence of this tells you that you have actually bilayer structure, right? So you see these modes, you can see this is the shear mode and this is the breathing mode, and that kind of concludes. And now the question is, you can again look into this, and let us say we want to identify where is 2H and where is 3R. Now the central question here we want to address, suppose you have a 2H WS2 over 2H WS2, what will be the thermal conductivity? And you have a 3R WS2 and a 3R WS2, what will be the thermal conductivity? And one can also think 2H versus 3H2, because each of them would have a different combination, because there will be correlated electrons, and that could actually change the properties because of the electron phonon couplings very drastically or very differently, I would say. So, what is important here, how to distinguish from the 2H from the 3R phase? One of the marker is actually the FWHM, or the width of this A1G mode, and you can see for the 3R phase, this is what we found. If the phase is 3R, then the width is much lesser, which is only 4.5 centimeter inverse, and if it is 2H phase, it is about 7.5 centimeter inverse. So, that is a marker to tell you whether you got a 2H or a 3R phase, right. So, this is something that you can do, and then we did little bit of not we did actually, our collaborator from IIT Madras, Professor Nanda, who did this calculation of these different phonons of the A1G modes, and you can see here, if you look at the 3R versus 2H, their lifetimes are very different. Okay, you can ask me why the lifetime is different. It is quite clear, because the full width and half maximas are actually different. So, that would translate to different lifetimes, and one is smaller, the one is this thing. Now, this should, if you remember the thermal conductivity expression, the lifetime plays, there is a parameter of the lifetime, if you remember half CV L square tau. So, naturally the thermal conductivities are supposed to be different, and one can actually do similar modeling about the heat transport and find out what would be the thermal conductivity. And as I told you in the formula, the expression, you have two parameter, one is d omega by dp, the laser power coefficient of the Raman shift, and the temperature coefficient, and that is what you do here. This is for the 2H phase, this is for the 3R phase. So, one of them is as a function of temperature, this is as a function of laser power, and then you measure this d omega by dp and d omega by dt, and that is what is being used to calculate the thermal conductivity. And then we see that we have these values at different temperatures. This is the thermal conductivity, and this is what actually people who have done using MEMS and other techniques. So, it is not that bad, but it is slightly looks like little overestimated for both the phases, but what I want you to appreciate is that we are still able to capture using a simple technique like Raman scattering and able to measure the thermal conductivity of these kind of systems. Okay, and then of course, a lot of extensive understanding was done by calculating the electronic structure and how these electron phonons are coupling is happening, and how does that happen, affect the rates of different phonons, their lifetimes, and how the 2H phase is different from the 3R phase in terms of their phonon spectrum, lifetime, etc., etc. That comes into picture of modeling the system in understanding the different values of thermal conductivity. But you can see here, obviously the 2H phase has actually lower thermal conductivity compared to the 3R phase. So, I think I just try to tell you that okay, you can use this technique not only to measure the thermal conductivity of a low dimension system, which I started with a nanowire, but it can be extended to graphene, it can be extended to bilayers of graphene or bilayers of transition metal dichalcogenate coordinate things, similar systems, right. So, now I want to just switch the gear by twisting. So, there were a lot of discussion that has been happening in last 2-3 days in something called a Moer system, and these are people who have reported very interesting results, that you can go from a normal phase to a superconducting phase just by twisting angle, tuning the angle between different layers. So, and then these patterns are called Moer patterns, and there is very interesting correlated physics one can study, and then for fundamental as well as application point of view. So, I want to give you one example where we have used Raman in understanding the twist angle dependence and then the correlation between phonons, excitons and their interactions, right. So, this is a paper that we published this year in Advanced Material with Prasanna from IIT Kharagpur and his students. So, this is very rich, and this is amazing the way these samples are grown. One has to appreciate. You can see this is actually a lateral hetero bilayer. Remember, in the earlier case I just talked about WS2 and WS2. Here it is laterally, there are different materials in the lateral direction, and in the vertical direction there are different materials and they are stacked. So what you see, there are different systems, MOS2, MOSC2, WS2, WSC2. So you can see that there are regions here, I think it is marked 1, 2, 3, 4, I don't know if you can see, and this is the different peaks, and you can see it is quite, I would say insane in terms of the way it has been stacked in all directions, vertical as well as the horizontal directions. And what exactly is the question that one can address here is that can you control simultaneously the twist angle as well as the combination of different materials, in this case the different transition metal dichalcogenides, to do what? To tune phonons, to tune excitons and their collective interaction, that means phonon exciton, phonon electron, electron phonon coupling, etc. So this is a very rich system where one can actually exploit these kind of systems to understand many different attributes, not only correlated physics, thermal transport, electron phonon coupling, and several other attributes that can be understood using this system. So this is quite complicated and insane system, but this has actually turned out to be lot of interesting results here. Sorry. So this is the system that I just mentioned, and I don't know if you can see this 1, 2, 3, 4 basically tells you which region is what. So it's basically you have one TMD, then you stitch another, then you stitch another. On top of that there are other things. So you can, wherever they overlap, and by the way it is not easy that you can just stitch them. Most of them are accidental, but you have to identify what is what, and then the twist angle is again you just measure what is the angle that you got. It is not easy, but the question is if you understand their physics, maybe you would be able to, one day you will be able to tune and then get the desired property. So that is how things work out here. Sorry, I think there is some issue here. Yeah. So now you can see if you go from the WS2 and WSC2 system, and what you do here, you keep on changing, I mean again it is not we keep on changing, you basically explore regions where different twist angles are there, you measure that. So you can see the Raman spectra is very different based on the twisting angle, okay. And as I said, there will be lot of correlated electrons, electronic effects at play, for which the spectra is very rich, and one can explain why the spectra using valitronics and stuff like that. I will not do that. I just want to tell you that just looking at the spectrum at different twist angle, the spectrum is different, and we understand individual thing, but when you put one over the other at different hetero bilayers, how this is being different, and that is because of this Mohr interaction, and there are different electron interaction at play. That is what this does. Okay, something is not right here, and you can actually do a lot of analysis using Raman of different peaks, A1G, E2G, etc., and see how their Raman shift actually changes as you change this twist angle. And this is an analysis, and you can identify which are these modes which have maximum enhancement in their intensity, in their frequency shift, and then you identify, can you correlate with certain properties, let us say the mechanical properties or the thermal properties, and this is what actually gives you a lot of interesting aspects. So here actually I have shown you a particular mode which is WS2 and WS2 and at a various twist angles, and you can see how the spectrum actually changes, and one has to understand the phonon spectrum, that is the dispersion relation, to understand this. But if you look into this, this twist angle, for different twist angle, this 1L, this is the line width actually. The line width does not change much, but if you go into the MOS2 to MOSC2 system, you can see there are new peaks, there is a diode splitting that occurs, and that actually explains these results. And again, as I said, one can do valitronics, valley physics to exploit these electrons getting trapped in local minima landscapes, and this is where the photoluminescence measurements tells you that how with different polarizations you can get different photoluminescence response with the circularly polarized light, etc. And one can do the second harmonic generation, which is actually done, which I am not showing, and that shows many interesting aspects of this kind of hetero bilayers that can be probed Well, I just spoke about Raman in detail, but that's not the only technique. You need to combine with photoluminescence. In this case, we have also done second harmonic generation. But the idea that I wanted to bring here, that a simple technique can actually provide you a plethora of advantages, which otherwise actually is quite challenging with other experiments. And so you can actually determine the layers, you can determine the polytypes, you can determine the defects, you can determine, I mean, lot of them. So I will quickly summarize. So these are the different systems, and we have been working on graphene a little bit, then transition metal dichalcogen quite a bit, mexin also we have done, which I did not present of course. And to understand the effect of layer number, strain, doping, defect, interlayer and band structure, and we have several of these articles that has been published. But today what I talked about is not any of these. I basically wanted to add 3 points in this. So one is we are able to tell about the polytypes by looking at the Raman spectrum, the intensity and the FWHM, and we could also look into the thermal transport, how to measure the thermal conductivity and thermal how heat is transported in this kind of systems, that is also possible. And at the end, well, somehow it is not there. So we could also do this twistronics, where how changing different twist angles, how the physics can be probed at a different scale, which phononics is something that that I discussed towards the end of my talk. So this is what we have been doing. We use Raman spectroscopy. This is one aspect of it, but we use for studying phase transitions, even studying minerals, earth sciences, etc., many other. But this is a major activity that is happening. So with this, I thank you for your attention, and looking forward to questions.
Thank you, Professor Kalam. Thank you. So open for questions now. Yeah. So there's your questions.
Yeah.
Thank you, sir.
Thank you very much for a nice talk. I have a question about thermal conductivity of your.
Yeah.
So, do you use the suspended sample or the soft tissue?
So in this case,
Yeah.
this is okay. So if you are referring to the silicon nanowire,
No, the
the
bilayer.
bilayer sample. These are all on the substrate. They are not suspended. So therefore, one has to also correct something called the interfacial resistance. Okay. So these are actually the numbers that we quoted, where the interfacial thermal resistance has not been taken into account. Yes, I must have mentioned, but that's a good question. But yeah, if you want to really calculate, then you have to do the modeling. What kind of, because it's a dielectric, silicon, then SiO2. So what would be the contribution of the dielectric medium towards the thermal conductivity? That has to be separated. That has not been done in this case. Yeah.
To refer the paper, the advanced material, the Sergio Barberi from Spain.
Yeah.
That we basically suspended sample to.
They are doing suspended thermal. That's right. That's right. Yes.
Okay.
Yeah.
So give the mic.
Hi, thanks Sunam, this was nice talk. Although I'm a bit worried about the thermal conductivity part of it.
Yeah.
And rather more from conceptual point of view.
Yes.
So when you're looking at this photon interaction, you're basically probing the Raman active mode, the acoustic modes which are responsible for your heat carrying, sitting at the gamma point, and majorly do not necessarily need to thermalize in case of 2D materials with the optical phonons that you are probing. So how do you reconcile this fact that if they are not in thermal equilibrium, while you are using single laser, you are in active non-equilibrium state. So committing something with respect to change in the temperature and then assessing thermal conductivity might not be accurately telling you what exactly it is. I mean, in some case, if it does thermalize, that's a pure coincidence.
Yeah. So that's a very important question, and I must. I have no reasons not to agree with you. There are a couple of things for the benefit of the audience I just want to tell you, because all things are nice to talk, but these are matter of details which need to actually be seriously dealt with. The first thing is, I have been talking here all Raman modes which are optical phonons, and as you mentioned, large part of its heat is actually carried by the acoustic phonons. Okay, so how do you deal with it? That is one question. Second question is it actually a equilibrium system or it's a kind of a non-equilibrium system? I don't think that's the problem here, because you wet enough so that the system is stabilized. But yes, when you look at the density of states, what we have seen, there are certain systems where the optical phonons plays as important as a role like the acoustic phonons. That is why maybe in some cases we are actually quite close to the experimental values, okay, but not necessarily that's a norm, that I must agree. And having said that, every technique has its own pitfall. I cannot tell, okay, this is the best technique. So you have to always benchmark with other techniques, and the idea is actually to collect lot of data from different samples and then compare. Then you tell, okay, now we have enough data to tell. So these are kind of in an early stage where this is we can take. Okay, so we can tell that, okay, this is an alternative which can be used, but any experiment, there are always sources of errors, and that has to be extensively discussed, which perhaps because of your question I am glad actually we are able to address. But yes, there are questions that remain. It's not as innocent as I presented, for sure. Yes.
Okay, yeah, if no more questions, let's thank you again.
Yeah, thank you. Thank you.
So much.